Here's some review problems. Or evaluate.
Alright, I say we start with the.
I wouldn't do that at all.
Kate, I feel like you're correct. I mean, I like that. I like that.
Okay, you guys, 90% of the time limits can be found by direct substitution. Okay, but here, you plug in a 2.
It's undefined.
It's undefined. Why is, I mean, other than that, obviously this is a rational expression, you can't divide by 0. Why is it undefined? If we were to graph this right here,
There would not be a point.
there's a vertical asymptote running right through x equals 2, right?
Yeah.
So, I know this has been a while, but you got to think, does that necessarily mean that the limit doesn't exist?
No, because it could be a point.
It could be a hole. If this was a removable discontinuity, can we remove the x minus 2?
No.
So this is not a removable discontinuity, but if it were, then it could just be a hole, and the limit would exist if it approaches the same point from both sides. Alright?
It also exists if they're both infinity in the same direction.
But exactly, this limit could exist if the graph looks something like this. Ooh, that's a terrible one. If the graph looks something like this, then what is f of x approaching as x approaches 2? On both sides, it approaches. So if this is what the graph looks like, what would the answer to this be? Infinity. But if the graph looks something like this, then what would you say? You would say the limit doesn't exist. Okay? Is this coming back to you a little bit?
Yeah.
And how do we know then if the limit is infinity or if the limit doesn't exist?
We graph it.
You could graph it. Alright? We could take a look at what this graph looks like. 3 divided by quantity x minus 2. What does it look like?
Oh.
So what do we say the answer to this is?
No.
The limit does not exist.
Doesn't exist. Now hold on though. What if I change the problem to this? Does this look familiar?
Yeah, that's the right.
Yeah.
Coming from the right.
There's a right-sided limit coming from, it's a one-sided limit coming from the right side. So if we take a look at the graph again, coming from the right side, approaching 2,
Infinity.
this limit exists, right? And what is it?
Positive infinity.
Positive infinity. Had we approached 2 from the left side, the limit would have been negative infinity. Okay, this was section 1.5, so it was a while ago. So what we're doing is similar to this. It's section 3.5, limits at infinity. So let's get started with the actual lesson. Limits at infinity. As a matter of fact, let's use that same graph that we just had. If we consider the function f of x equals 3 over x minus 2, let's just draw a rough sketch of the graph here. We know that we had a vertical asymptote at positive 2. Remember though, these rational functions, they don't just have vertical asymptotes. What else do they have? They do have horizontal, and these are hard to remember. They're not hard to find, but they're hard to remember sometimes how to find them. It depends on the degree of the numerator compared to the degree of the denominator. Does this sound familiar?
Yeah.
This numerator has no variable, so it's considered degree 0. This one is a degree 1. So the denominator has a higher degree than the numerator. What does that mean about the asymptote? The horizontal asymptote in that case is 0. Okay. So what did this graph even look like? So
Zero power is not 1.
yeah, really the reason it's considered to be degree 0 because it does have a variable, but it's just x to the 0 power, which is just 1. So this graph roughly looks something like this.
What is the degree of bigger than the L?
Then it has a slanted, it could have a slanted asymptote. We'll talk about that here in a second. But that's a pretty good drawing, I guess, of that function. We talked about a limit where f of x or x approaches a certain integer, but what if I wanted to talk about this limit, the limit as x approaches infinity, positive infinity, of 3 over x minus 2. So we're traveling along the graph now, and we're traveling out to positive infinity. Where is f of x heading? Towards 0. Okay. So we would say that the limit, it has a lot to do with the horizontal asymptote here. The limit as x approaches infinity of that is 0. Okay. This is talking about the end behavior, essentially. And as x gets sufficiently large, and in this case tending towards positive infinity, this graph is approaching 0. Okay. Does it ever reach 0? No, but it gets closer and closer and closer to it. It approaches 0. So as x approaches infinity, f of x approaches 0 is how you would read this. Okay. Now, let's draw another graph here. And then draw this dotted line right about here. Quite often, a graph will approach this kind of an asymptote, but it'll oscillate like this. So do your best to draw that. Okay, even in this case, where the function's graph is oscillating, okay, as long as that oscillation continues as x approaches infinity, the limit exists, and the limit would be this horizontal asymptote right here. Does that make sense? It might be with a trig function. Okay, it's very possible.
If the function crosses over.
Yeah, functions can cross a horizontal asymptote. They cannot ever cross a vertical asymptote, but they can cross a horizontal asymptote. Limit as x approaches infinity exists, and the limit would be equal to whatever the value of that horizontal line is. Okay? Yeah, pretty much. So here's a definition that ties this to a horizontal asymptote. The line y equals L is a horizontal asymptote if the limit as x approaches negative infinity of f of x is equal to that line L, or it could be approaching the other side, positive infinity. The limit as x approaches positive infinity of f of x is equal to that horizontal line L. And then a quick theorem. So let C be any real number and R is a positive rational number. So C is just a number. This is a constant. C stands for a constant. What's the degree? If it has no variable, what do we say the degree is? Degree is 0. This has a degree that's larger because it's x to the r power. So if the degree is larger on the denominator than it is on the numerator, what do we say about the horizontal asymptote? 0. So if we were to graph something like this, a constant divided by x to some power, the horizontal asymptote would be 0. So as if we try to find the limit as x approaches infinity or negative infinity, where would f of x approach? 0. So the limit as x approaches infinity of this kind of an expression, a constant divided by x to the r, always equals 0, because that's where the horizontal asymptote is going to be. Okay. Another way you could think about this if you wanted to, you don't have to think about it this way, but as you start to plug in larger and larger and larger values of r, because x is approaching infinity, right? What's going to happen to this value down here? This is going to get bigger and bigger and bigger and bigger and bigger. Much, much bigger, but c is going to remain constant. So what's eventually going to happen to this ratio right here? The fraction is going to get smaller and smaller and smaller and smaller and smaller. To eventually, what's the fraction approaching? The fraction itself, or this ratio itself, is approaching 0 because you have a small number divided by an increasingly larger number. So that ratio is just going to get closer and closer to 0. So, does that make sense?
Yeah.
You can think about it that way. Okay. So let's just get into some plug and chug examples here. Find the limit as x approaches infinity of the function 5 minus 2 over x squared. Well, one of the properties, maybe I should have reviewed this as well. Do you remember one of the properties, if you're taking the limit of the sum or difference?
You can take one of these individually.
Exactly. You remember that property? You can take the limit of each one individually. Is this ringing a bell?
Yeah.
So you can split this apart into the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Ooh, here's another property of limits I should have reviewed with you. What happens if you take the limit, regardless of what x is approaching? What happens when you take the limit of a constant? What is 5? If we were to graph just y equals 5, what is that?
It's always 5.
It's a horizontal line where the y values are always 5. So as x approaches infinity, what's the y value always going to be? 5. So the limit as x approaches infinity of 5 is 5. That's one of the properties of a limit. If you take the limit of a constant, it's equal to that constant. But then this here,
This is where things get crazy. So the horizontal line is supposed to be 0.
that's just an illustration of that property right there. We have a constant divided by x to some integer power.
So it needs to be 0.
So the limit of that is,
And then you 5 minus 0.
the limit of this is 0. That's an illustration of this theorem right here. So the limit is equal to 5 minus 0, which is 5.
Dang, look at us.
Okay?
I like 5 minus 0.
Here's another one. Limit as x approaches infinity
There's no limit to
of 2x minus 1 over x plus 1.
quotient rule. Let's do it.
Yeah. If we're doing derivatives, maybe.
That's actually exactly what I thought. I was like, no.
One of the properties that we learned a long time ago is you could take the quotient of these limits.
I would just plug in infinity.
So if we did the limit as x approaches infinity of 2x minus 1, and then we took a separate limit as x approaches infinity of x plus 1, we could divide them, but
Infinity plus 1.
what's the problem here? What's the limit as x approaches infinity of 2x minus 1? Or what's the limit as x approaches infinity of x plus 1? Well, the graph of 2x minus 1,
Oh, it doesn't
that's just a
have,
straight line, right?
It doesn't have a number.
So as x is approaching infinity, what's y approaching?
Infinity.
Infinity. So the limit of this is infinity. Now this graph down here, x plus 1, that's just a line like that. So as x approaches infinity, what's y approaching?
Infinity.
Infinity. So if we try to use that property we learned back in chapter 1, where we divide each limit, it would be infinity divided by infinity.
So it's 1.
No.
It's 1.
No.
Mr.
That comes out to be the answer.
This results in infinity divided by infinity. This is called the indeterminate form. Infinity divided by infinity is called indeterminate form.
Yeah, because the one up there would be approaching infinity faster than the one below.
Yeah, you could think about it that way. Yeah, that's true.
I'm
What
gonna
if they
do
were-
infinity faster than you. You'll never get there.
So here's what we need to do. Instead of just taking the limit right now, let's just consider this expression 2x minus 1 over x plus 1.
What?
This little trick you guys are going to want to make a note of. Whenever you get this indeterminate form, this little trick helps quite a bit. If I multiplied this by something over itself, wouldn't that be okay if I multiplied a fraction by the same thing on top and bottom?
Yes.
Multiply by 1.
Just because you're essentially multiplying by 1. So what if I did 1 over x over 1 over x? Is that okay?
Yeah.
You do what you do.
I feel like that's just getting things complicated, though.
So that's going to be 2x minus 1 over x plus 1 over x.
Oh.
You multiply by the circle.
Just an X.
You could, but you'd end up with this.
Same thing.
You'd end up with the same thing starting. Yeah. Okay, this is getting a little funky, so just bear with me for a second.
Okay, I got a red
If we just took this by itself, 2x minus 1 divided by x. 2x minus 1 divided by x. Isn't that what that means?
Yeah.
So let's just go through the long division here real quick. How many times does x go into 2x?
2 times.
2 times x is?
2x.
Okay. Draw the line, change the sign. So the remainder is negative 1. So this is 2 minus 1 over x. I know it's been a while since you've done long division of polynomials, but does that make sense?
Oh.
The quotient is 2 because that's the result of the division, and then once you get your remainder, you put that over your divisor. You follow?
Over your divisor.
You've got your remainder here over this.
Yeah.
So this turns into that. I need to make sure we all agree on that.
I agree.
How did I go from 2x minus 1 over x into 2 minus 1 over x? How did that happen?
You divide.
He did the long division.
Yeah.
Could
Could you just
see it that
just split it into two
and
terms?
the x's would cancel out?
I guess, yeah.
And you just
Actually, didn't even-
see that it splits rather than doing polygon division.
Or you could do it this way. Ooh, me likey. Check this out. That's a great thought. Here's version 2.0. This is like the iPhone 6 now after we had the
Write
iPhone
that
5.
down.
What if we just did 2x minus 1 as this? That was so much easier. X is canceled, so we have 2 minus 1 over x.
Yeah, that was money. That's a money way.
That was better. And then do the same thing for this one. Instead of x plus 1 over x, just do x over x plus 1 over x. And that turns into 1 plus 1 over x. So we have 2 minus x over 1 plus 1 over x. And now we take the limit of this. The limit as x approaches infinity.
Now we'll put it in the
Yeah, we can plug in infinity on this one.
I'm just thinking with the limit, doesn't that being 2?
Oh, you're jumping ahead. Yeah, it does.
What?
Hold on now.
Skipping steps.
Yeah.
I don't like when people skip steps.
That kind of shit.
Now let's do the individual. Let's do the individual limits of a numerator and a denominator. So if we take the limit of 2 minus 1 over x, and then we take another limit as x approaches infinity of 1 plus 1 over x, now we can just use that theorem.
Oh, because that would be 1 over 2.
So let's just deal with this limit right here. What's the limit as x approaches infinity of 2? It's just 2. And what's the limit of x approaches infinity of 1 over x? So that's 2 minus 0. And then down here, the limit as x approaches infinity of 1 is 1. And the limit as x approaches infinity of 1 over x
0.
is 0. So this is 2 minus 0 over 1 plus 0, which is 2.
Holy Moses.
Now, Josh was noticing right off the bat, the original form of this was 2x minus 1 over x plus 1. We couldn't find the limit by using direct substitution because we got that indeterminate form. But right up here, this definition, the limit of a function is equal to its horizontal asymptote, if it has one, right? So if we were to consider the graph of this is degree 1 and that's degree 1. So what happens with the horizontal asymptote if they're equal degree?
Take the ratio.
You take the ratio of the leading coefficients. 2 divided by 1.
Why didn't you just tell us in the first place?
Yeah,
That was fun.
Why did you lead us on a wild goose chase?
That was kind of fun.
That was fun, but still.
But the horizontal asymptote,
Gingerbread man.
We did catch you.
the horizontal asymptote is 2. So what does that mean about the limit?
Back and shoot across the road. Not today.
Hey, what does that mean about the limit? The limit has to be 2 because the horizontal asymptote is 2.
Won't go down.
Okay? You with me still? One last example, then I'll hand out the review we can start working on now. We're almost done. So evaluate. Just try these as quick as you can, just for the sake of practice. 2x plus 5 over 3x squared plus 1. For part B, limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1. And then for part C, limit as x approaches infinity of 2x to the third plus 5
That's a quick example.
over 3x squared plus 1. These really are quick. Just got them.
Rick is big for about
Alright, so this one here. This is a degree 1 numerator, this is a degree 2 denominator. So the denominator has a higher degree than the numerator. What does that mean about a horizontal asymptote? So then the limit equals 0. The horizontal asymptote in that case is 0, so the limit as x approaches infinity is equal to 0. Okay. For this one, yeah, they have equal degree. It's an x squared divided by an x squared. In that case, if it's equal degree, you divide the leading coefficients. So this horizontal asymptote is 2/3, which also means the limit as x approaches infinity is 2/3. Okay. This one here, the degree on top is bigger than the degree on the denominator.
Always equals 1.
Yep.
Do you remember what happened in this is back in pre-calculus? What happened when the degree of the numerator was bigger? There wasn't a horizontal asymptote. It could be a slant asymptote, but there was no horizontal asymptote. If there is no horizontal asymptote,
Then it's just undefined.
then there is no limit as x approaches infinity. Okay? Yeah. This one has no horizontal asymptote. So limit doesn't exist. Okay? Now these next two, I just want you to draw a picture just to have a reference. You aren't going to have ones like this on your test, but just so you can have an idea. Limit as x approaches infinity of the sine of x versus the limit as x approaches infinity of the sine of x over x. Just draw these real quick so we can be done with this. You guys remember what the graph of sine x looks like? Starts at the top or starts in the middle? Starts in the middle and it goes up to 1 and then down to -1. So it is a terrible picture, but Anyway, you get the idea, and it goes in both directions. Oh, that's ugly. Now over here for the sine x over x, I want you to draw this picture.
Okay. Whoa.
Ooh. Let me start over with that one.
It's smaller.
Yeah, shouldn't it be a sine graph?
It's the sine of x divided by x. So,
Start at 1, or is it?
yeah. But there's a hole at 0 because x can't equal 0 technically.
And what would be the limit of sine of it?
Well, that's what I wanted to talk about. I need to amend slightly a statement I made at the very beginning. This limit doesn't exist over here, the limit of x approaches infinity. Because as you travel along this graph horizontally, as x approaches infinity, what's happening to the graph? It goes up to 1 and down to -1. Up to 1, down to negative. Is f of x approaching anything concrete? No, this limit does not exist. Okay? So I think I might have mentioned earlier that if a graph oscillates, then the limit exists. But it's not just that it oscillates. It has to be getting infinitesimally closer and closer. The oscillations have to become smaller and smaller. Does that make sense?
Yeah.
This one here, it does still oscillate, but every time it repeats a cycle, doesn't the oscillation get smaller and smaller and smaller? Okay? As you travel along this graph then, as x approaches infinity, what are you approaching? You're approaching 0, so this limit exists. And the limit is 0. So just keep that in mind. It doesn't just oscillate. The oscillations are getting smaller and smaller and smaller. So anyway, that's the end of that.